Okay, so here I have an example for a continuous data set where we have a range of values for our x variable. And in this case, this is the distance from a particular factory that we wanted to test. And then we have our y values, which is still the dissolved oxygen levels at those particular distances. So I've set up everything the same way that I did in the bar graph with the discontinuous example. However, this time I just have more data points and I did some additional calculations for the standard deviation and the average, but everything is the same. I also changed, though, the type of graph that I use. And so in the data, you can see I selected an XY scatter, okay? Not a line, an XY scatter. And this allowed me to compare my distance from the factory to the dissolved oxygen levels. And this is the result. The other chart element that you'll need to add is a trend line. So if I go to chart design, I can add chart element, trend line, and in this case, I'm going to pick a linear trend line, or I could pick exponential. Depends what makes most sense to your graph. And it looks like this could be appropriate, or it even seems like the linear can be appropriate. Either way, it doesn't matter. It doesn't matter for this example. I made up these numbers. So looking at the data now, I want to do my overall patterns and trends. Well, as the distance from the factory increases, the dissolved oxygen levels increase. The dissolved oxygen level is lowest at 0 meters away from the factory and highest the further I get away at 250 meters from the factory. So that's the first thing I want to look at, patterns and trends. Then I want to look at how big are my error bars. Well, my error bars are all different, which makes sense because I used the data sets to calculate the standard deviation independently for each data set. So I want to see, where are my error bars the largest? I can see that my error bars at 0 meters distance from the factory and the furthest one away from the factory at 250 meters are the largest error bars. I can discuss, why might that be? Maybe the factory has different pipes that bring water or wastewater out of the factory, and it's mixing unequally in the river at those points. Maybe there are sections where there's more pollution than others, decreasing the dissolved oxygen levels. You can come up with reasons why the data varies more in these sections versus the other sections. And remember, the variation in the data is the standard deviation. How far are the values from the average? The closer they are to the average, the more reliable our data is. So you're going to look at that. And then we're going to look at, well, how much do the error bars overlap? Well, the error bars look like they might almost overlap from 0 to 50 meters. That could signify that there's not a significant difference between the dissolved oxygen levels at 0 meters versus 50 meters. Here we can see the error bars might slightly overlap. That would indicate that, here we go, we can see a little bit better. So they don't overlap there. Here they do overlap. That would indicate that it's not significantly different between those 2 points. As we go up, we can just discuss each error bar in relation to the next to see, is there a significant difference? And finally, I can compare my initial and my final dissolved oxygen levels, the dissolved oxygen at 0 meters and the dissolved oxygen at 250 meters. And I can see there is a significant difference between those two groups. The error bars do not overlap. There is a significant difference between the dissolved oxygen levels at the factory outlet into the river versus 250 meters away. And then you can base your analysis around how strongly does the data support this conclusion. And then you can talk about the reasons for variation in your data, and then you can move on to your evaluation.